So in math, a lot of times you're used to maybe doing some of this in geometry. You guys would have done, remember some of the isometric transformations you did would have been things like translations and rotations and reflections. Give me a thumbs up if you remember doing that stuff. Okay. And then you did some non-isometric transformation. Actually, the only one you probably did was dilations, right? But those are examples of transformations. We're going to do similar stuff here. But as we do this, I want you in the back of your mind to be thinking that this is just one good, effective example that's useful of a technique that we use in math all the time. And it extends all the way up to the very highest levels of math, like probably the most sophisticated math that humans have developed at this point would be the math associated with string theory, which is it's a theory that's evolving in the area of physics. And it's so complex that there really are only about a dozen people in the world who have been able to really understand it. I mean, only the absolute most brilliant minds in the world really can even put this together and make sense of it. But within string theory, they do some crazy things. You know, string theory maintains that our universe, in addition to the three extended dimensions in our universe, there are an additional 6 dimensions that are really tiny dimensions that are tightly curled up that you don't really see on a macroscopic scale, but they have pretty profound impacts for how, they would explain, for example, the way gravity works. They would explain a lot of the properties of our universe, and they do something the other thing that it does that's so significant is it's able to knit together the physics of the very small, which is described by quantum mechanics, and the physics of the very large, which is described by general relativity. And we'll take a day some other time and talk more about this, but I just wanted to bring an example to mind here. There's one of the things that we do in string theory. There are these 7-dimensional, incredibly complex topological math, but there are these 7-dimensional, entities called Calabi-Yau spaces, and it's a lot of what you do in string theory. It's topological, so it would do things like you would say that the important properties of an object are how many closed loops does the object contain. And so, for example, if you were to look at a coffee mug only has one closed loop, and that's the handle, right? You can put your finger completely through the handle, and it emerges from the other side, and you can touch your finger with your other hand then, right? You can't do that through the bottom of the cup, even though it's hollow. You can't go through the bottom of the cup, so it's only got this one closed loop. Are you guys familiar with the aerobie? It's like a frisbee with a hole in the middle. Kind of, you can throw them really far. Have you ever seen those? Or a hula hoop would be another example, right? A hula hoop or an aerobie would be other examples of topological creatures that only have one closed loop, right? There's a hole in the center. And so you could say then that topologically speaking, a coffee mug is much more similar to a hula hoop than it is to a drinking glass. Now, that seems crazy, right? Because a coffee mug looks almost exactly like a drinking glass. But the fact that the drinking glass has no closed loops and the coffee mug has one means that the coffee mug and the hula hoop are essentially virtually the same thing, and the glass is something completely different, right? Well, in this topological math, when physicists want to do things like they want to be able to predict from the mathematics what gravity should look like, or what the nuclear strong force should look like, what they find is in this incredibly complex math that they can do a transformation where in one kind of a space they can make sense of gravity, but they can't make sense of some other parts of our universe. But then when they do this complex transformation, they can maybe make sense of the nuclear strong force in this other transformation, but not gravity. And it all has to do with moving back and forth between these 7-dimensional spaces. And it's just incredibly complex math. I mean, super dense. But even there, this is kind of a long-winded example, but I want to make this real for you. Even there, the things that they're doing are just extensions of the stuff we're going to be doing today, right? Where you're just transforming basic functions to put them into forms that are more useful for you to answer a specific question. And as we move forward, our next topic, after we get through this one, we're going to be talking about quadratic functions. And you will remember probably from Algebra 1 that we have various different forms of quadratic functions. We talk about a standard form. I don't know if you remember this, a standard form and a vertex form. And maybe even, I don't know if you guys ever talked about an intercepts form or a factored form. We'll talk about all this stuff. If that's not familiar, that's okay. We're going to go through this all from scratch. But I want you to be thinking about how, in the back of your mind, about this conversation we just had, I want you to be thinking about how when we look at these different functions, they're all different representations of the same thing, a parabola, right? The graphs would all look the same, but each of them has their own unique purposes. Each of them allows us to solve a different type of equation and extract different information about the parabola, right? And so this is something we do in math. We go back and forth between different forms of the same thing, okay? Anyway, I think it's important sometimes to be looking ahead and thinking about, why we're following the path that we're following in math. And I want you to kind of see why we're doing the things we do in the order that we do them. Okay, let's jump into something more concrete here. Let's remind ourselves what it means to do these transformations. Okay, so what happens if inside the function, if I'm adding or subtracting a number directly to the input x? Do you remember what that does? What does this do if I add some value to x inside the function? Can anybody tell me? Okay, I'm seeing people pointing to the left. That's correct. Okay, so that's going to shift us. So that's shifting us h units to the left, right? And then what must this do? If we're subtracting h from x, that's shifting us to the right then, isn't it?
Isn't it the other way around?
No, it's not actually. It's not. It's when you subtract h, you're shifting to the right, and when you're adding h, you shift to the left. It's kind of bizarre. And I'll show you why it's that way. I'm just not going to do it today. But we can come back after break, and I can show you. I can show you mathematically. It just takes, it doesn't take a lot of time, but we're not going to have time to do it today. I can show you mathematically why it has to be that way. But for now, I'm just going to tell you just to kind of accept that and remember it. And you would have seen that. It's a little bit, it's a little counterintuitive. But when you pull up these Desmos, in fact, let me just pull one up right now real quick, just to reinforce this a little bit. So if I pull up, where's the H? There we go. So if I pull up the H, transforming H example, look what happens. Notice up here, P of x is our parent function. It's an absolute value of x. And f of x is defined as the absolute value of x minus h. So if I am subtracting a positive value, look what happens. It's scooting to the right. So this would be the function f of x equals x minus 2. And look what it did. It scooted everything to the right by 2. Now if I make it 3, it scoots it right by 3. Everybody see that? If I make h a negative value, then that's going to look like, for example, here, this would be the absolute value of x minus negative 4. Well, that looks like an x plus 4. Okay, look, it scooted it to the left. So my short answer to this, Maria, is what we're always going to do when we write our transformations, when we write down the transformation corresponding to a horizontal shift, we're always going to subtract the value of h from x. And that way, a positive value of h means we're scooting right, and a negative value of h means we're scooting left, because we're subtracting the value from x. Okay, everyone give me a thumbs up on that. Does that make sense? or thumbs down or thumbs sideways if it doesn't make sense. Okay, so what I mean by that is if we were to go back to, let's go back to here. Like if I had something like this, like if I had our standard form is going to be if our parent function is p of x, then if we write f of x equals p of x minus h, in this case, h is telling us, and so this is really, well, h is telling us the amount of the horizontal shift. So if we plug in a value, like if we say h equals 2, then that means I'm shifting right by 2. But look, here's the important thing. We're subtracting h from x in our transformed function. Okay, we always write it down that way. What we're going to, let me skip ahead here just for a second. Like if I skip up to here, this is how we're always going to represent all of our transformations. We're going to start with this general expression of our transformation of p of x, but notice that h is always subtracted from x inside the function. Okay, and that in that way, positive values of h mean we're moving to the right, and negative values mean we're moving to the left. And I don't want to jump the gun here. We'll talk more about this when we look at examples. But if I see something like, for example, let's say, I can go back now. If I see something like this, like if my parent graph, if I'm looking at, let's say, a square root function, for example, okay? If f of x equals the square root of x minus 2, my question to you is, what value of h is that? What value of h is that if my parent graph is the square root of x, but f of x is the square root of x minus 2? What's the value of h, my horizontal shift? Say it again. It's positive 2, right? Because 2 is the value that's being subtracted from x. So h is positive 2. That means we're going to the right by 2. Okay, let's look at another one. What if we have g of x equals the square root of x plus 3? Now, what's my value of h in this example? It's negative 3, right? Because h is what's being subtracted from x. And would everybody agree that x plus 3 is the same as x minus negative 3? So h would be negative 3, which means we're going left by 3. You see how that works? Okay. Okay, so h is a little confusing. You kind of almost have to think about that as h is doing the opposite of what the sign seems to be telling you, what the operation seems to be telling you. When I have an x plus h inside my function, seems like I ought to go to the right, but no, I'm actually going left because remember, I'm subtracting the h value from x. When I have an x minus a number, it seems like I ought to go left, but it's the opposite of what I might normally think. I'm going to the right. K is much easier. K gives us our vertical offset, right? And think why. If I have some function and I just add a value to the function, aren't I just picking all of the y values up by that amount? The output is changing by that amount, right? And so if I'm adding K, that's going to be a shift upwards. So K is exactly what your intuition would tell you. And if K is negative, well, we're shifting down. Okay, so let's try something like that then. So if g of x is the absolute value of x plus 9, well, we all know what our absolute value parent graph looks like, right? That's going to be, let's real quickly, let's just graph that. Our absolute value parent graph, it's one of the easiest ones to graph. So what should that look like? What's our absolute value parent graph going to look like here? Abby, if I'm graphing p of x equals the absolute value of x, what can you tell me?
It starts at the origin
Okay, good.
at a V.
And it looks like a V, good. And so if I go over 2, how far up am I going?
How far up?
Yeah.
You're gonna go up 2, right?
Yeah, there you go, exactly, right, perfect. Okay, so if I want to create some anchor points on my graph, I know the slope is 1, so I always go over as much as I go up on my parent graph. And going backwards, I just get the same negative slope, right? So I'm going to get points there, there, and there. You get the idea, right? So there's my parent graph. So which of these would make sense then, Adelaide? If g of x is the absolute value of x plus 9, which one, A, B, C, or D, would be the one that makes sense for our graph? I can tell you're going to say it. You almost said it. Okay, now, but I'm adding the value outside of the function this time, right? It's not in the absolute value. It's outside of the absolute. Yep, so it's up, exactly. So it'd be B, wouldn't it, right? We're going to vertically shift by positive 9, and so our answer would be right there. That's our graph, isn't it? If we subtracted a number outside of the function, it just would have shifted it down, right? Okay. How about, I guess I gave you the answer on this one. Which one would we get here? Well, I forgot to cover up that one. So do we see why this one is shifting left? Explain to me why we're going left with this one, Alan. Looks like we're going left by 3, doesn't it? How come? Oh, I can't hear you. I'm going to skip you, Alan. Looks like your mic's not working. Andrew.
Okay, so h is 3, and h is actually a negative because it would be x minus negative h.
Okay, so what's the value of h then?
3?
No,
Negative 3?
it's
Negative 3?
it's negative 3, right? The value of h is negative 3 because g of x, if we're looking at horizontal translations, we always subtract h from x, right? So the value of h here is negative 3 because that's what we're subtracting. So that's why we're going left, because the horizontal transformation is negative. Horizontal translation, I should say. Okay, everybody give me thumbs up, thumbs down on that one. Okay, all right, good. Okay, let's go back a little bit. So now let's look at dilations. Okay, so the value that we're multiplying by the function, now think what that's doing. And let me go back to my cool little transformation tools here, right? I've spent so much time making these, you might as well play with them a little bit, right? So here was our k, right? If we're adding a value to the function, doesn't that just mean that the output values, the y values, are changing by the amount that we add? We just talked about that, right? So if I add 1, it goes up by 1, add 2, add 3, it just goes up. If I subtract, add negatives, it goes down, okay? What about A? Okay, look what A does here. If I multiply my function by a, then I am multiplying all of the y values, right? Well, if my y value is 0 to begin with, if I multiply that y value by something, it just stays 0. But look at the other ones. They all change proportionately, don't they? If my y value used to be 1, if my multiplication factor, right, out front, we'll call it the stretch factor, becomes 2, well, look what happens. My y value increases from 1 to 2. If my y value used to be 2, I'm multiplying that by 2, and now it's becoming 4, right? The y value, the y coordinate, is it's just the distance from the x-axis, isn't it? Right? So the vertical distance from the x-axis is what is being multiplied by a. Everybody see that? Okay. All right. So then what could we say here? If a is greater than 1, if the absolute value of a is greater than 1, what's going to be happening to my function? If the absolute value of a is greater than 1, it looks like, I mean, you tell me, what's going on with my function then? Okay, so it's people are doing with their hands, they're showing me that it's getting taller and skinnier. Yeah, it's being stretched vertically, isn't it? Well, what happens if I multiply by a value that's less than 1? Well, look what happens. Now it's getting squashed vertically or compressed vertically, isn't it? Right? The y values here have been multiplied by 1/2, and so it pushes those points down vertically. You can see, if you watch this, when we do these vertical dilations, the points, notice that they do not move horizontally. It's right. It's like they're relegated to move on these vertical wires. You can only slide the points up or down on the wires as it gets stretched vertically. So it's purely a vertical effect. It has no impact horizontally on the function. It looks like when you stretch a function vertically, it looks like it's being compressed horizontally, but it's not, right? It's just that the points are moving up vertically, so it gives it that illusion, right? There is, not to confuse you, but there is a horizontal dilation factor that we could talk about, but I'm not going to do it this year just because I've done it in the past. It doesn't really add that much to the conversation for now, and it just takes additional time. But I will tell you this. You can also introduce a horizontal dilation factor, which is it ends up being multiplied by x inside the function instead of being multiplied by the function outside of the function. And the two can be made to do exactly the same thing. So just as you move forward in math, know that there is an alternate way to look at this. It's just more complicated. But we could compress a function horizontally, and that does turn out to be equivalent to stretching it vertically. Okay, there is a way you can do that, but it's just, like I say, we don't have time to do it. Okay, what about this? So, well, let's write that down first of all. If the absolute value of a is greater than 1, then we're increasing our y values, and so that corresponds to a vertical stretch. If the absolute value of a is less than 1, so it's between 0 and 1, then that corresponds to a vertical compression. Okay, what do you think happens if a becomes negative? Let's take a look at that. Based on what I just told you, this should be a pretty straightforward prediction. I told you that a is what we multiply by the y values, right? So let's take, for example, the point that has a y value of 2 on our parent graph. Starts off with the coordinates x equals 2 and y equals 2. What do you think is going to happen if I make a equal to -3? What do you think? Andrew Saxton, what do you think is going to happen?
The slope will go downwards.
Yeah, okay. We're taking the current parent y value of positive 2, and if we multiply that by negative 3, we should get a y value of 2 times negative 3, which is negative 6. And look, that's what happens. Okay, so it's really no surprise if we just look at this as being a factor, the dilation factor. It's what we're multiplying by the y values. We could say then for negative values of x, or of a, what are we doing to the function? Like if I picked a equals negative 1, what did I do? What did I do to the green parent graph? I reflected it, sure. I just reflected it, right? And so almost invariably, these Algebra 2 books, and this is okay, but these Algebra 2 books talk about if you multiply the function by negative 1, it means we're reflecting it around the x-axis, right? So we're reflecting over, I should say. But I would encourage you to just think about this. Don't even think about these as separate processes, right? That's really just all the same case. We're just multiplying the y values, which are just the values of the function, by a, whether a is positive or negative, right? It's really just the same thing. If a is negative, you're still doing the same process, aren't you? Okay, let's just practice that for a second. If I scoot forward, how about something like that then? Okay, so first of all, if f of x is the parent graph, Chloe, what's the value of a here? What's our dilation factor for g of x? It's negative 1. Good. Now notice what we're doing with these, right? We're consistently looking at the parent graph and comparing it to the transformed graph, and we're identifying right away. We're just trying to identify what are the values of the parameters a, h, and k. And once we know what those values are, we can make the appropriate transformation to the graph, right? But it's all about figuring out what are the numerical values of those parameters, a, h, and k. And then we'll practice what we do with them. So what would be the correct graph here then, Dawson? Are you here? Can you hear me, Dawson? Is everything working okay for you? Your tech working? Technical issues maybe. Talib, how about you?
Would it be B?
It is B, right? Everybody see that? And how come it's B? Because look, we've just multiplied all of the y values by A, which is negative 1, right? So for example, this value right here, we'll just pick one of these as a reference. This value right here in our parent graph that has coordinates 2, 4, what should the coordinates of the transformed graph be?
-2, -4?
No. Close. -2, -4 would be over there.
2, -4?
2, -4, right? Because we're only multiplying the y value times a. So we should be at the point 2, -4, because it's a reflection of that. And if we do that to all the points, then we just end up with this reflected graph that looks like that, right? So there it is. Okay, how about something like that? Kendall, what's the value of a for this one?
2, maybe?
No. Look at that again. Our parent graph is f of x. Remember, A is what occupies the place in front of the parent graph, right? It's what we're multiplying by the parent graph. So what are we multiplying by our function here?
1/2.
1/2, there you go. So that's our dilation factor. So that's what we're multiplying by all of the y values. So these, look, there's a horizontal line, all of the y coordinates of every point on that function, and we'll look at maybe those 3, right? There's 3 kind of anchor points for us that we can refer to. Well, the value of 2 is being multiplied by 1/2. Well, doesn't that mean that those y values are all going to end up down here instead? So there's what my graph should be. So what do we get there? I guess that's B. Everybody agree? There's a tendency for people to want to shrink this horizontally too, but we don't, right? All we're doing is we're just shrinking the y values. We're compressing them vertically this time. Okay, thumbs up, thumbs down. Okay. All right, last issue. I'm adding something. This isn't part of the regular notes, but I'm adding this for you guys. So what happens here if we multiply x inside the function by -1? Anybody care to hazard a guess what that does? Let's investigate. Let's just think about this for a second. Let's say I've got the parent graph. Let's just take the square root of x, for example, right? So we've got these points, these reference points at 1, 1, and then we go over 4 and up 2, right? Okay, let's do a couple things. Let's look at this first. Let's take, if that's f of x, or that's p of x, how about for parent graph? Let's make f of x negative p of x. Okay, so then if I input into p of x, if I input a 1, I output a 1, but I'm multiplying that by -1, right? So what did that do? Well, it's as we expected. That made the y value -1, right? We already talked about that. If I input a 4, my parent graph outputs a 2, but I'm going to multiply my output by -1, so that makes it a -2. So it's down there, right? And so we saw that we reflected over the x-axis. Now, what's going to happen, though, if we make a new function? Let's call it g of x, which is p of -x. What in the world is that going to do? Okay, so if I were to input an x value of 1, what would I get back? If I'm inputting an x value of 1 into g of x, I get p of -1. Is my function even defined for -1 if it's a square root? Can I take a square root of a negative number? Can't do that, can I? Right? I can only take square roots of non-negative numbers. That's one of our 2 fundamental rules for real numbers. We can't divide by 0, and we can't take an even root of a negative number, right? Okay, so there is no point at x equals +1. Okay, but let me ask you this. My parent graph, if I plug in a +1, I get back a y value of 1, right? Well, g of x is defined as p of -x, right? So if I want to end up feeding my parent graph a value of +1, what number would I have to plug in for x if x is being multiplied by -1? right? We always feed a function, whatever's inside the parentheses. If I have f of x, right? If I calculate something like f of 4, the function is just seeing that input value. It doesn't care how we get it. We just feed it an input value and it processes it and spits out an output value, right? Well, if I plug in an x value of 1 there, my g of x is going to see p of negative 1 times x. When I plug in an x value of 1, my parent graph is seeing an input value of negative 1, which it can't handle, right? So before we go here, my one question to you is, what value of x, give me an example of a value of x that I could feed in so that my parent graph is processing a positive number. There we go. Like, what if I plugged in a value of negative 1, right? Then look what's happening. My parent graph is processing negative 1, which is positive 1, right? Well, p of positive 1 is 1. So if I feed it a value of negative 1, I'm getting an output of 1. So look what it did. It put it over there. If I feed it a value of negative 4, we're multiplying that input by negative 1. So negative 4 is positive 4. I get an output of positive 2. So what was the effect of that? If I multiply x inside the function by negative 1, what did it do?
Reflect over the y-axis.
Yeah, that's it. It just reflects it over the y-axis. Does that make sense? Okay, so we didn't get through all this stuff. If you guys want to get started on the assignment, you could probably get started on the assignment. Okay, I think if I'm remembering the assignments, you could do almost all of 2.6 practice, or I'm sorry, 3.2 practice 2. And you could even do a couple parts of 3.2 practice 3, but don't spend inordinate amounts of time trying to get this done. I will shift the due dates and we'll wrap this up after break. But if you want to go in and just reinforce this a little bit, go ahead. But this takes a little more time, and it's really a fun lecture. We'll deal with it after break. I'm looking forward to it, but don't waste a lot of time trying to figure it out on your own. We will talk about it after break. I'll extend the due dates. I better let you go. Have a wonderful break. I'll be here after school if you need anything. But if I don't see you, just really enjoy your break. Spend good time with your family and relax a little bit. See you guys.